Before the transformer, processing sequences in AI was largely about building models that handled information step by step, but this approach had some real bottlenecks.
I remember from our earlier case on sequence models how RNNs especially struggled with really long sentences, and that step by step is the core issue for speed, right?
Exactly. They process one word, then the next, accumulating context, but that makes parallel processing difficult, slowing training significantly. This paper proposed a radical shift.
It's summed up right in the title. Attention is all you need. This paper argues that instead of complex, recurrent, or convolutional networks, attention alone is sufficient.
So instead of a hidden state passing information along, each word gets to look at all other words simultaneously. That's a huge conceptual leap.
It is. The transformer architecture achieves this by dispensing with recurrence and convolutions entirely. It truly relies on nothing but attention mechanisms.
That's a bold claim for an architecture. How can it capture sequential information without any recurrence or convolutional layers to process neighborhoods?
We've explored attention in cases TCM 183004 and TCM 033002. Today, we're seeing attention not as an add-on, but as the fundamental building block. It's based solely on attention mechanisms.
So the attention mechanism we've already learned about is now the whole story, not just a part of it. That's a powerful idea. What's the main benefit?
The major gain is that these models are more parallelizable. Each part of the input can be processed simultaneously because there's no inherent sequential dependency.
So the entire input sentence can be processed at once. That's a massive shift from word-by-word processing for speed.
This parallelization translates directly to speed. The paper states it's requiring significantly less time to train. For instance, days instead of weeks for state-of-the-art results.
That kind of speed up changes what's possible for model development. But does parallelization come at the cost of accuracy?
Quite the opposite. They showed it was improving over the existing best results on challenging machine translation tasks. The parallel architecture also yielded better quality.
So faster training and better results. That sounds like a breakthrough. But how does it achieve that quality without traditional sequence modeling?
It's not just about speed. It's about providing superior in quality results. The attention mechanism provides a more holistic view of the input, leading to richer representations.
It's amazing that stripping away complexity and focusing on one core idea could yield such an improvement. But what does this architecture actually look like?
That's exactly what we'll explore next, breaking down the transformer's components to see how this attention-only model functions. To understand how attention alone can achieve this, let's look at the transformer structure, starting with a high-level view from the illustrated transformer. Think of the transformer first as a model as a single black box. You feed it a sentence in one language, and it outputs a translation in another. This black box view simplifies the complex internal processes, but it hides the intricate architecture that allows for parallel processing and contextual understanding we're about to uncover.
Right, the basic idea of a sequence-to-sequence model. But we know there's something revolutionary happening inside this black box.
Opening that box, we find two main parts, an encoding component and a decoding component. The encoder processes the input, the decoder generates the output.
This encoder-decoder structure is familiar. But what makes the transformer's version unique? Is it just the attention mechanism?
Precisely. Instead of just one, the encoding component is a stack of encoders, usually 6. Each encoder processes the input from the layer below, applying its own self-attention and feed-forward networks. This allows for increasingly abstract and rich representations of the input words, building hierarchical understanding rather than just simply refining them.
So it's not just a single layer of attention, but multiple layers building on each other. How does each encoder actually process a word?
Each encoder starts with a self-attention layer, a layer that helps the encoder look at other words in the input sentence as it processes a specific word.
This is where the magic happens, right? It's not just looking at the previous word, but all the words in the sentence at once.
Consider the sentence, "The animal didn't cross the street because it was too tired." If we ask, what does it in this sentence refer to, a human understands it's the animal.
And traditional models often struggled with that kind of ambiguity, especially over long distances. So self-attention solves this?
Yes, self-attention allows it to associate it with animal. When processing it, the model can weigh animal as highly relevant, effectively linking them.
This simultaneous association across the entire input is what gives it such powerful contextual understanding, right?
Think of how maintaining a hidden state allows an RNN to incorporate its representation of previous words. Self-attention does something similar, but without the sequential constraint, allowing direct links.
So instead of an RNN's cumulative memory, self-attention builds a direct, learned connection between any two words, irrespective of their distance?
Exactly. And after the self-attention layer, the outputs of the self-attention layer are fed to a feed-forward neural network. This is another crucial part of each encoder.
A feed-forward network? So a standard neural network on top of the attention output? What's its role after all that attention work?
This feed-forward network applies a transformation independently to each position. It provides additional nonlinearity and allows the model to process the attended information further, adding more layers of feature extraction. Think of it as refining the contextual information gathered by self-attention into richer, more abstract representations.
Crucially, the word in each position flows through its own path in the encoder. While there are dependencies within the self-attention layer, these paths are largely parallel. However, since self-attention itself has no inherent sense of word order, we need something more.
You mean if you jumble the words, the self-attention would still work the same way? But word order is critical for meaning. How does the transformer handle that?
That's where positional encoding comes in. Before the input embeddings enter the first encoder, we add numerical vectors to them that encode the absolute or relative position of each word in the sequence. This way, even though the self-attention processes words in parallel, each word's embedding carries information about its original position, allowing the model to distinguish dog bites man from man bites dog. Now that we understand the encoder's main components, let's dive into the detailed mechanics of self-attention, how it calculates these associations using query, key, and value vectors. To move from intuition to mechanism, we need to understand the three core vectors in self-attention: query, key, and value.
So every word gets its own Q, K, and V, and these are learned projections of the word embedding itself?
Yes, exactly. For each input word's embedding, we multiply it by three distinct weight matrices, one for query, one for key, and one for value. These matrices are learned during training, and they project the embedding into these new Q, K, V spaces. This is how the model creates these specialized vectors. This article directly asks, what are the query, key, and value vectors? Think of query as, what am I looking for? Key as, what do I have to offer? And value as, what information do I carry? While these analogies are helpful for intuition, remember that Q, K, and V are simply learned numerical vectors. Their meaning emerges from how they interact mathematically, rather than them literally asking or offering anything. We'll see that math next, which clarifies their functional role, but the abstract search analogy breaks down if you push it too far.
That analogy helps. So query is like a search term, key is like a tag on a piece of information, and value is the actual information itself.
Next, to find out how relevant other words are to our current word, we calculate a score. This is done by taking the dot product of the query vector with the key vector of every other word.
So if my query vector aligns well with another word's key vector, that dot product will be high, indicating strong relevance. That's a clever way to measure similarity.
If we're processing it, we take its query vector and find its dot product with the key vector of animal, street, tired, and all other words. This is scoring each word of the input sentence against this word.
So each word gets a score for every other word, indicating how much attention it should pay to them. This is how the it to animal link is formed.
Before the next step, we divide the scores by 8, which is the square root of the key vector dimension. This scaling helps stabilize gradients during training.
That's an important detail. Without it, some dot products could become too large, making training difficult. It's a normalization step then.
After scaling, we pass the result through a softmax operation. This normalizes the scores, turning them into attention weights that sum to 1, representing a probability distribution.
So now we have a clear set of percentages telling us how much each word should influence the current word's representation. Animal would get a high percentage for it.
Exactly. The softmax score determines how much each word will be expressed at this position. Now for the final crucial step, we multiply each value vector by its corresponding softmax score. This effectively weights the information each word carries by how relevant it is. Then we sum up all these weighted value vectors. This sum is the output of the self-attention layer for our current word. It's an aggregate of information from all other words precisely weighted by their relevance.
That's it. So a single self-attention head produces a new context-rich representation for each word based on all other words. But I remember hearing about multi-head attention in the transformer. What's that?
You're right to ask. Instead of just one set of QK and V projections, the transformer employs multiple attention heads, leading to multi-headed attention. Each head learns different projection matrices, allowing it to focus on different aspects of the input simultaneously.
So different search strategies or perspectives on the same sentence? Like one head looks for grammatical dependencies, another for semantic relationships, and another for factual connections?
Precisely. Each head can learn to attend to different parts of the input, capturing a richer and more diverse set of relationships. The outputs from all these heads are then concatenated and linearly transformed, providing a comprehensive contextual representation for each word.
This simultaneous association across the entire input sounds incredible, but does it have any downsides? Doesn't looking at every other word get really expensive for long sentences?
That's a sharp observation, Maya. The core limitation of basic self-attention is its quadratic computational cost with respect to sequence length. If a sentence doubles in length, the computations can quadruple. This makes processing very long texts computationally intensive and memory hungry. Another important point is that self-attention by itself loses the order of words. Since it processes everything in parallel, it doesn't inherently know if cat sat on mat is different from Matt sat on cat. That's where positional encoding comes in, adding numerical information about each word's relative or absolute position to the embeddings before they enter the transformer. This is a crucial add-on that enables the transformer to retain sequential information without recurrence, but it's not part of the self-attention mechanism itself.
This powerful architecture, particularly the encoder with its multi-head self-attention, laid the groundwork for a new generation of language models like BERT.
Now, let's connect the transformer to one of its most famous descendants, BERT, or bidirectional encoder representations from transformers.
So BERT is built on the transformer architecture, but what does bidirectional mean in this context, and how does it achieve that deep context understanding?
Great question. Unlike earlier models that process text left to right or right to left, BERT leverages the transformer's encoder, which, by dispensing with recurrence and convolutions entirely, inherently allows every word to attend to every other word in the input sentence simultaneously, regardless of their position.
This means that for any given word, BERT's encoder uses self-attention to associate it with both preceding and succeeding words right from the very first layer. This creates truly bidirectional context representations, not just a combination of two unidirectional ones.
So instead of just seeing animal and then it's always seeing it in the full context of the animal didn't cross the street because it was too tired from the start. That's a powerful difference for understanding nuance.
Exactly, and because the transformer is more parallelizable, BERT can be trained on massive amounts of text data very efficiently. This pre-training involves specific tasks designed to build its deep, bidirectional understanding.
What kind of tasks? Is it still translating or something different?
One key task is masked language modeling, where BERT predicts intentionally hidden or masked words in a sentence. Because it uses the full bidirectional context to do this, it learns incredibly rich semantic relationships. Another is next sentence prediction, where it learns to predict if one sentence logically follows another. These tasks, applied over huge text corpuses, imbue BERT with its remarkable language understanding.
The result is a model that achieves deep bidirectional context understanding, far exceeding previous state-of-the-art models on a wide range of language understanding tasks. Just as the original transformer was improving over the existing best results for machine translation, BERT did the same for tasks like question answering and sentiment analysis.
It's clear how much of a leap the transformer was. It didn't just speed things up. It enabled a completely new way for AI to truly grasp the meaning and nuance in language.
Indeed, from its foundational parallel attention to the deep contextual power of models like BERT, the transformer truly reshaped the landscape of AI.
And it all started with a radical idea that attention is all you need.